Alright, today we have a viewer requested video, Student Attendance Record 2, Leetcode 552. So the problem is as follows. We're asked to create some sort of attendance record using just the letters A, L, and P. And basically they're going to give us an n value, which is the length of this attendance record, or length of this string. And we have two conditions. So first of all, right off the bat, right, this is basically like a combinations problem. Using these three letters, we're going to just create as many different combinations as we can. But there's two conditions. The conditions are we can only have one A. It says that we can have strictly fewer than 2 days absent. So we can only have one or zero A's. If we have two A's, it's invalid. And then we have the student was never late for 3 or more consecutive days. So that means that if there's three or more L's in a row, it's invalid. But I'll show you what we're actually gonna we're gonna change this this line a little bit. We're gonna capture this state a little bit differently in our code, and I'll get to that in a second. So basically, the first thing we can think of when we have some sort of combinations problem is some recursive tree diagram, right? So basically, with recursion, this is a very easy problem. And actually, you can do recursive DFS plus memoization in some of the other languages. For Python, for some reason, it times out for me. So I actually had to turn this into a bottom-up DP iteratively. So I'll go through both approaches. So this might be a pretty long video, so please just bear with me for this. But I truly think that you'll be able to learn a lot from looking at both the recursive implementation and as well as the iterative implementation. So let's take a look at both. So first of all, with the recursive implementation, let's keep track of a few variables, right? So we can pass along some different variables for each each recursive call. We can pass along some parameters that will help us to capture the current state that we're in, right? So the three variables that we'll want to keep track of are obviously the n value, which is the length of the string. So we can start at we can pass in initially the n value of whatever it is. Let's say it's 2, so we can initially pass in 2, and then once n comes down to 0, that'll be our base case. That'll be our terminating condition. Once we reach 0, then we can terminate. So then a second variable we should keep track of is the number of consecutive L's, and obviously that's exactly what it sounds like. So basically, this means that consecutive L's, this is only relating to L's that are at the end of the string. So if we have some string like A L L P, this has 0. In our state, we're going to consider this as having 0 consecutive L's. If it ends with LL, however, like in this string, then our consecutive L's will be 2. If it's like this, then we'll have 1 consecutive L. But once again, like I said, if it doesn't end in L, then the consecutive L's will be 0. Even though we have 2 consecutive L's here, we'll consider it as 0. And basically, the idea is just that once we have 2 consecutive L's, we're not going to want to we're not going to append another L to it. So basically, we're going to prevent creating invalid strings as opposed to creating invalid strings and then cleaning them up. It's kind of like prevention versus cleanup. We're going to prevent the invalid strings from ever even being created. So once we have 2 L's, we're not going to append another L. And same with the case of A. If we already have an A, we're not going to ever append another A to it. So we're going to just prevent these two conditions from ever happening. And then once we hit the base case of 0, and obviously if it successfully hit the base case of 0, then we know that we should return a value of 1. Indicating that string was valid. So basically, so in this recursive tree, I can kind of show you what I mean by that. So at the base, when we first start the recursive solution, we'll have an empty string, right? We'll have nothing, and we'll have two letters left to add. We'll have 0 consecutive L's, and we'll have 0 A's. So once we're at this state, we have 3 options, right? We can append an A to it, we can append an L to it, we can append a P to it. If we append an A to it, obviously, so everything in this level has 1 less character remaining, right? Because we added 1 character, so we have 1 less character remaining. So that's what the first one is for all of these recursive states. And then here for A, there's 0 consecutive L's, right? There's 0 consecutive L's. There's 0 L's. It's ending with 0 L's. And then once we come here, this variable indicates that we do have an A. So I'll show you how we handle that later. So this other case, this other state is we have an L, right? So obviously I already mentioned the first one. The second one signifies that there is 1 consecutive L. So it's ending in a consecutive L of 1. And there's 0 A's. Then with P, obviously we have 1 less character to use. And then there's 0 consecutive L's. It's not ending with any consecutive L's. And it does not have an A. So then let's see from this A, what are the different choices we have? So since we already marked that we have an A, this combo AA will actually never be created. We will never create that combination. We're going to prevent it from happening. So what we're actually going to create is we only have 2 choices. Since we already have an A, we only have 2 choices now. We can only add an L or we can add a P to it. So from this A tree, we can only have AL and AP. And then, this AL would look something like there'd be 0 characters left to append, and then we'd have 1 consecutive L, and we'd have 0, and we'd also have an A. So yeah, anything that has a 0 has 0 characters remaining will just immediately return 1. So we'll kind of sum up everything, all of those ones, and then that'll be our answer at the end. Right? So then let's take a look at this over here. So with LA, this would be, you know, the state, like the numbers associated with it would be 0 characters left to append to it. There's 0 consecutive L's, and there is an A. So yeah, so all the rest of these combinations are all valid. So we can see that when we have 2, when we started with n value of 2, we'll have 8 possible combinations to create. So none of these are breaking those conditions. The only one that was breaking the conditions were this AA at the beginning, but like I said, we're never even going to create that, because once we have one A, once we already have this field marked as 1, we will never create another A. We won't allow it to happen in our code. So you can see that this AL will return 1, AP will return 1, LA will return 1, LL will return a value of 1, LP will return 1. So there's eight different valid combinations that all return a value of 1. So our answer will we'll sum up all those, and we'll return 8. So I can kind of show you the recursive code here, and then just to help you get a better understanding of it, but just know that we're going to eventually have to turn this into bottom-up DP. So for the recursive solution, so let me take out this cache. In Python, I just use this like little shortcut cheat thing, a cache. But let me show you what it would look like if I actually had to do a memorization. So basically, I just have to say like, so let me first explain this code, and then I'll show you what the memorization looks like. So first of all, we have a mod, and then we're going to return the result of this DFS call. So the main logic is all here in this DFS. This is just it's like the main method calling it. So here's the DFS, right? So we have 3 states. Like I said earlier, we have the n value, we have the consecutive L's, and we have the has A or doesn't have A variable. So the base case, like I said, if we get down to 0, then we know it's valid. All the invalid stuff will be discarded before it gets down to 0, before the n gets down to 0. So we can rest assured that whenever it does get down to 0, we can always return 1, indicating that it was a valid sequence. So then we have a temp variable, and then we append, you know, we do some whatever addition to it, like plus equals to it. So basically, these are the 3 main conditions, right? These are the 3 main options, right? At each state, we can either add an A, L, or P, but the A and the L can only be added in certain circumstances, right? That's why I have it. That's why I have it wrapped around this if statement. The P will always be an option. Even if there's an A, even if there's an L, even if there's 2 consecutive L's, you can always add a P to it. So that's why the P is not wrapped in some if statement. So we can only add an A if we don't already have an A. So that's what this statement is. If we don't already have an A, then we can add an A, and then we'll mark this flag as true. So then the next iteration around, we'll never be able to pass through this logic again. So then we won't be able to add another A to it. And you know, so basically, yep, same thing with the P, or sorry, same thing with the L. So we can only add an L if there's less than 2 consecutive late. If there is 2 consecutive late, then we will not add another L to it, because then we'll have 3 L's, and that's invalid. So we can only add an L if we have 0 consecutive late or 1 consecutive late. If there's 2 consecutive late, then we will not be adding another L to it. And then, like I said, with the P, it can always be added. And then at every step, you always just want to mod it, just to make sure you're not doing some overflow. And I think, yeah, that's pretty self-explanatory. So this temp variable will be returned at each call. So basically, you can imagine from here, we make the 3 DFS calls on A, L, and P, and then A is going to make 2 more calls to L and P. Like it's gonna. So if we're at this A, we're not gonna hit this condition. We're going to hit this condition, and we're going to also hit this condition. So then we'll return the answer to those calls, and those calls will have A, L, A, P. So this A will return 2, this L will return 3, this P will return 3, and then we'll have all this summed up in a temp. And so basically at each recursive call, if you want to use memorization, this is what it would look like. So you will just do cache of n consec late has A equals temp, and then you just return the cache, or you can return the temp, doesn't matter. Since these 2 values are the same, cache of this and temp are the same, you can return either of them, doesn't matter. And then basically you'll also have to add, if this n consec late and has A combination is already in the cache, then we can just return cache of n consec late has A. Right? So this is the memorization. These 2 lines, and then adding this to the cache. These 3 lines allows it to be a recursive DFS plus memo DP problem. But even then, this still will time out actually. So actually also, this is the same thing as me putting cache. So this is so powerful in Python. Just putting this cache will allow you to get rid of those 3 lines, and it will cache it'll cache all these results for you. It'll cache the combinations of n consec late and has A for you. Okay, this is a continuation of the first part. So in this part, I'm gonna go over the bottom-up DP approach as opposed to the recursive DFS memo. So let's talk about states. So there's 6 total possible states for any given sequence. Any sequence can be categorized under one of these 6 states. So how do I know there's 6 states? Well, like we said before, there's 3 variables that we had right here, right? So the ones that we're going to be using to calculate the state are the consecutive L's, which can only be 0 consecutive L's or 1 consecutive L or 2 consecutive L's, and then also the has A or doesn't have A, which can only be 0 or 1. So 3 times 2, that gives you 6 total states. So let's talk about these states and show you what they look like for the DP bottom-up approach. So first of all, we're going to have 3 different, we're going to capture 3 dimensions, right? So the first dimension is going to be the n value, so same dimensions as the recursive implementation. So we have the n value is the first dimension, second dimension is consecutive L's, and third dimension is there an A or is there not an A? So let's take a look at these 4 bottom states first. These are actually easier to understand, and then the top 2 states are a bit more challenging to grasp. But let's talk about these. So the last state has 2 consecutive late and 1 A. That's what this current string must contain to be considered in state 6. If you want to be in state 6, you have to have 2 consecutive lates and 1 A. So like we said earlier, the consecutive late means it ends in L, right? So to have 2 consecutive lates and to have an A, this is a string that's considered in this sequence, or in this state, right? So the only way to have gotten from this state was from APPL, and then we add an L. So what state is APPL in? APPL is in the state 4, which has 1 consecutive late and 1 A, right? We have 1 A here and 1 consecutive late. So that's why dp of I 2, 1 is equal to whatever dp of I minus 1, 1 was, right? This is state 4 right here. Okay, let's take a look at state 5. So to get to state 5, so state 5 has 2 consecutive late and 0 A's. So it's essentially the same thing as state 6, except there's no A at the front. So that could look something like PPLL. The only way to get to PPLL was from PPL. And so that's why, yeah, so what state is PPL in? PPL is in the state 3, which has 1 consecutive late and 0 A's, right? That's why dp of I 2, 0 is equal to whatever dp of I minus 1, 1, 0 was. Okay, so let's take a look at state 4. State 4 has 1 consecutive late and 1 A, so that could look something like AL, right? So APPL, same thing. So the only way to have gotten to APPL is from APP. So what category is APP under? APP is under the state that has 0 consecutive late and 1 A, so that's state 2. So this came from state 2. That's why dp of I 1, 1 is equal to dp of I minus 1, 0, 1. Then let's look at state 3. So state 3 has 1 consecutive late and 0 A's, so that looks something like PPL. To get to PPL, we had to have came from PP. So what category is PP under, or what state is PP under? It's under state 1, which has 0 consecutive late and 0 A's. So then comes the slightly tricky part, which is state 1 and 2. So let's start with state 1, because there's 3 possible ways to get to state 1. There's 6 possible ways to get to state 2, so that's going to be a little bit more challenging, and it'll build upon your understanding of state 1. Okay, state 1, we must have 0 consecutive lates and 0 A's. So what are the 3 different ways we can get there? So we can get there from something that has 0 consecutive late, so like P. So from P, we could add another P to get to 0 consecutive late, 0 A's. From PL, so we could come from something that has 1 consecutive late and then add another character onto it, which will which will reset the consecutive late, right? So PLP is a valid sequence for this state, right? It has 0 consecutive late and it has 0 A's. But the previous state was something that had 1 consecutive late. So we can do the same thing with 2 consecutive late. So we can come from a state that has 2 consecutive lates, but just add a P to it, and we'll be right back to 0 consecutive lates and 0 A's, right? So we have 3 different states that are possible here. The next one is state 2. This has 0 consecutive lates and 1 A. So in addition to the 3 possible states, so it's slightly different, but basically, you're going to be adding the 3 states from before, and you have the option to have an A as well. So let me show you how that works. So basically, we can come from the state P, which has 0 consecutive late and 0 A's, and then add another P. Add an A. So this PA sequence matches the condition of 0 consecutive late and 1 A, right? We have 1 8 and we have 0 consecutive lates. So then we can do another one where we can come from PL actually. PL has 0 A's. It has 1 consecutive late and 0 A's, which is state 3, right? And then if we add an A to it, now we're meeting this condition, 0 consecutive late and 1 A, right? PLA has 0 consecutive late and 1 A. So same thing with PLL, right? We can add an A to that as well, and then we're in this state. We're in a valid sequence for this state, right? And then we can do the same thing for already has an A, right? We can come from something that already has an A, as opposed to adding the A to get here. So if we already have an A, then that'll be the other 3 conditions, condition 2 here, condition 4 here, condition 6 here, right? Those already have an A. So we can come from those 3 states which already have an A, and then, add some P to it or something, right? We can come from an A that already has 1 L, 1 consecutive L, and then add a P. We can come from something that has an A and 2 consecutive L's, and then add a P. So there's 6 different ways to get to state 2. So this these are the different states and the transitions to get to each of these 6 states. So you might be thinking, oh, so how does any of this actually help me figure out what the answer is to n equals 2, right? So the answer to n equals 2 is going to be stored at dp of 2. dp of 2, whatever, dp of 2 has 6 different states, right? It has 0, 0, dp of 2, 0, 0, dp of 2, 0, 1, dp of 2, 1, 1, right? It has all these different states, dp of 2, 0, 1, has all 6 states, right? So the sum of all these 6 states will be the answer to dp of 2, which is what we're looking for. So, any of these 8 combinations here can fall under one of these 6 categories. This one is category, has 1 consecutive late and 1A, so it's category 4, right? So all these summed up, the answers to each of these subproblems summed up will be our final answer. So the only thing we have to really think about at last is we need base cases. So how do we get the ball rolling? How do we initialize something that will not just give us all zeros at the end, right? So we need to have some sort of base case. So the base case we can just have is, we can pretty much just hard code it. When we have a string of length 1, so this will be for dp of 1, 0, 0. When our string is length 1 and we have 0 consecutive late and 0 A's, how many different possible valid sequences are there? There's 1 valid sequence. And then we have dp of 1, 0, 1. So let's see. dp of 1, 0, 1. So let me just copy this over. So these are the base cases. And so let's just take a look at them real quick. Okay, so if we have a sequence of 1 and there's 0 consecutive late and 0 A's, there's only one way to do that, right? There's only one way, which is a P. So then we have 0 consecutive late and 1A with length of 1. There's only one way, which is that. Then we have 1 consecutive late and 0 A's. The only way to do that is with an L, so that's 1. So then we have dp of 1, 1, 1. So this means that there's 1 consecutive late and 1 A. That's not possible when the string is only length 1, right? To have something that's consecutive late, it must end in L. But to also have an A means that we must have had some A earlier. And we're talking about the base case here, which only has length 1. So the only way to have these two conditions of 1 consecutive late and 1A is to have at least a string of length 2, and that's not possible here yet. So this will return 0. There's 0 possible ways to do that with a string of length 1. So with a string of length 1, and we have 2 consecutive late, right? 2, first of all, we only have length 1. We can't have anything more than length 1, so that's also 0. And then same with this last one, it's also 0. So you can see that our base cases are 1, 1, 1, 0, 0, 0 for these 6 states. And then, so I can kind of show you the code here. Don't try to memorize the code, but just take a look at what you'll be doing. So basically, you'll initialize these 6 base case states, like I just showed you, and then you'll have a mod. You'll create the dp 3D table using n plus 1, 3, 2. Right? So dp of 0, when the first dimension is 0, everything will be 0. So you can have the base case start at 1 or 0, it doesn't matter. I think it just makes more sense to start the base case at 1. So then in my for loop, I start from dp of 2, actually. So just take note of that. And then, I'm modding at each step, and I already showed you. So dp of I, 0, 0 can come from 3 possible ways, right? It can come from when the previous one is also in the state 0, 0. It can come from when the previous one is in the state 1, 0. It can come from when the previous state is 2, 0, right? That's kind of what all of these are. And then this one has 6 possible ways to do it. This one has, these last 4 only have 1 possible way to do it. And then at the end, your answer will be stored in the last row of the DP, right? So the DP looks something like a 3D table, a 3-dimensional array. I don't know how to show you that, but basically just think about it like yeah, you'll have some 2D grid, whatever. I don't know how to draw it. Whatever, you'll have a 2D matrix, and then the last row will be, you'll have to sum up everything in the last row. Which will give you the answer to the final thing. So that's what I'm doing here. I'm summing up everything in the last row and in the last, yeah, whatever you call it, the last dimension. So yeah, so that is how you do it. I really hope that was a good explanation. I'm certainly not that great at bottom-up DP. I think that the recursive implementation is so intuitive and easy to do and easy to explain. And whenever I have the chance, I'll definitely use recursive DFS plus memo as opposed to bottom-up DP. The runtime is actually supposed to be about the same. They're both O of n time complexity, but for some reason their Python test cases or their whatever submission autograder is too strict for Python for this question, so it doesn't work. For C++ Java, you can just directly memorize this recursive thing and it'll work. But alright, hope you guys enjoyed this. Hope you guys learned something. Please give me feedback. If you didn't learn anything, just please give me some feedback. Please, just let me know what you think I can explain better next time, improve on. I'm going to try to buy some sort of iPad so I can start to do some drawing and draw some diagrams as opposed to typing it out. So hopefully that'll make my video quality even better in the future. But if you sticked around all the way until the end, then seriously thank you, and yeah, alright, bye.